Hello everyone, my name is Nitin Sharma from 4th year Engineering Physics IIT Roorkee, and today I am going to present my BTech project PPT on the topic of fMRI based biomarker detection. It is under the supervision of Professor Mayank Goswami from Physics Department IIT Roorkee and in collaboration with Professor Dr. Margaret Walter from Jena University, Germany. So the outline of the today's presentation is we will discuss actually four data sets and we will go in line from PSI MRI data set and the methods we applied which are domain adaptation and few shot learning and the Ketamine 2018 data set and the psychometric effect analysis on the Ketamine study. Then the CPM analysis, then OSC scope prediction on 2014 and 18 dataset, and in which we will further go to PCC, PSC regions and the 246 features we got and the gradient verification. Then finally, we will verify our results on the ketamine depression dataset. And then we will go to the conclusion and then references. So what is fMRI and how we can use it for biomarker detection? So fMRI is actually a non-invasive technique. So in which we do not need to insert some kind of electrode inside the brain. We just record the activity using the changes in the blood flow. So as the blood oxygenation, as some activity is happening in our brain, so the blood oxygenation demand in that region is actually increased. So we can see this bold response, which is blood oxygen level dependent signal. So we see this kind of a response in the fMRI image, and this is actually very highly correlated to the event related potential, ERP potential. And we can see the RMS value of the ERP potential in this yellow line and the bold signal in the orange line. So we can see these are actually very highly correlated. So for this study, we are focusing on the major depressive disorder. And why we are doing that? Because MDD is the most significant cause of disability and morbidity according to the WHO data. And it affects more than 264 million people worldwide. And also, till now, because of its heterogeneity in the symptoms, there is no precise clinical diagnosis and no regions on which a clinician can focus to diagnose someone with MDD, or there are no particular region on which some treatment medication can be focused. So the general outline for our this BTech project is we have this fMRI image. This is just a 2D slice of our brain, and we this is our 3D range. So we do some parcellations for the ROI extraction. So what does it mean? We have some predefined atlases, and a single this color actually represents a region from which we are averaging our signal. So this actually increase the signal to noise ratio, and these regions are made because they have a very similar functional region. So this particular part has a, let's say this has a similar visual function region, and these are divided into v1 to v6. So these are the bases of this ROI regions. So we extract the time series because this is actually a 4D signal. So we have these 3D images stacked together in a time. So this actually each time point is the average signal of a particular ROI across time. Then what we do, we find the functional correlation between the time series. So we have these two time series, so let's say 1 and 2. We find the correlation between them and we plot it here. Let's say it's point 2, and then between 2 and 3, and then we make a point here. So we do this correlation for all 200 cross 200. So this is our matrix size, and then we do it for all the subjects. And let's say, so we are here, we have this function connectivity matrix. So what we do, we actually, this is symmetric because the correlation between 2 and 1 is same as 1 and 2 for the time series. So what we do, we take only the upper triangle of this matrix, and we can take the lower one also because it is symmetric. So we have total of how many columns? 200 into 200 minus 1 upon 2 for a ROI atlas of 200 regions, which is equal to 19,900 regions. So for a single subject, which is our row, and we have 19,900 columns. So we have this MRI QC parameters, or let's say scanner parameters, which we want to remove the noise. So we try to fit each of these signal, which is a single column. using these noise parameters, and we want to regress out the noise and subtract it, and we got the final signals which we will work on. So for our first study, we have Psi MRI dataset. So this is how it looks. So we have 12 sites, and we have, this is the healthy control, and this is the major depressive disorder patient, and this is our total subjects. And these are the possible TR and TR count. So we can see how much heterogeneity each site has with very different ratios of subjects, and also the different TR and even the TR count. So first of all, we deal with the domain adaptation methods because we have different sites, so we want to remove the site effects. So in which what we do, we have, let's say, data from very two different images, let's say, one which have a black background and a white image and which is colorful. So if it is actually found that it is very difficult to test the data on a different kind of a data set and train it on a very different data set. Although, let's say, this is a text detection, a digit detection task. So although it is a digit detection task, but it is seeing that if we train it on this image, let's say all images which are black and white, and we test it on some other image which is colored, then the accuracy drops quite a significantly. So what we do, we try to model them into a same dimension, and we want to focus on the prediction of this, let's say, digit. And in our case, we want to predict our level as healthy control versus MDD, and also we want to minimize the source and target. We want to project in the same dimension. So in total, we employed around six domain adaptation methods, and I will discuss only two, three of them here. So let's say first one of them is discriminative adversarial neural networks, and we have this kind of a network which tries to increase the accuracy of classification accuracy and tries to decrease the site-wise differences. So this is the result for each of the sites. So site, I mean the different location from which the data was collected. So we can see, like, for some sites actually the accuracy decreased, but for many we can see a quite an improvement using this DANN analysis. And the other one is the choral alignment analysis. What we do, we have, let's say, this target dataset and source dataset which are in a different plane. So we tries to align them to a same plane, and we tries to minimize the differences between these sites, the data set, which is most probably because of the scanner effects, not because of the classification effects. So we can see by applying these domain adaptation methods for different classifier, we tested for different hyperparameters and different classifier. We can see the classification accuracy increases quite a bit for the domain adaptation method with the Gaussian classifier. And also we, for individual site, because this was the average across all the sites, the accuracy average, but for each site we can see quite an improvement. Let's say we have this target trained accuracy 76, and now applying the choral methods, we have a classification accuracy of 84.62%, and we can see similar increase in many of the sites. But actually you can see there is not that much increase in the accuracy, and this was because of some challenges in our data set. The first one, these methods actually introduced in the research paper are for the MNIAST and SVHN digit classification task, and in these we have a quite a lot number of data points, 70,000 training and testing and 90,000 training testing points, but here we have only less than 1,000 points. So because of this, it is very difficult to avoid this overfitting problem. So to avoid this problem, we introduce our self-introduced model. So these are actually very highly similar to this DNN, ADD, and deep coral methods, but we improved on one of the factors because of the limitation of our target data set. So we have a sufficient number of source domain data points, but our target, we have a single site. So the data points only vary from, let's say, at max to 100 data points. So for that, we introduced the four versions: only site discriminator loss, site discrimination and class loss, deep coral based loss, and also deep coral loss and site discrimination loss, which we will introduce in detail. So the first one is the only site discriminator loss. So in which what we do, we tries to just project the source and target domain into a one dimension. So what we do, so we have this gain like network. So this is our target domain and this is our source domain. So in actual we have this kind of an encoder for this target domain also, but in which in here what we are doing, as we have a very less number of target data points, let's say only 100. So we are not uh, changing it to some other domain, like not projecting it to some other space, because we do not have sufficient data to train our network. So we are keeping it as it is. But as we have sufficient number of data points for our source data set, like around 700, 800, because out of the let's say 12 sites, we have one for the target site and remaining 11 for our source site, and we will repeat this procedure for each of our each site as a target site. So we have our source site, and we tries to project in some the embedded dimension, which we tries to and which we tries to discriminate against the target data set. So what happens? We have this target site and the source site. Target site plane will remain as it is, and the source site will tries to shift the plane towards the target site. So we are not classifying here. What we are doing, we are projecting our source data to the target site plane to decrease the loss between them, so that they will be projected to a same plane, and then we will classify them. So this is our code for each component. Let's say for the encoder, we are making this encoding model to project them. This is our encoder model, this whole. And then we have our discriminator. So discriminator, what it tries to does, it tries to differentiate between the sites, and it will back propagate this loss. And then we will model them together, and while training our this model, we will do this as a false, the training data set. So what we are doing, first we will try to project them to a single site, and then we will train our discriminator to classify between target and source site. So it will create some loss function, and then we will make it as a false, and then again we will try to encode our source data to the target data set. So what happens, our discriminator will penalize if it is able to discriminate between target and source data set, which we do not want, so that's why it is penalizing. And then encoder will tries to improve upon that and will make our data set as much as less discriminable between target and source site. And then we will compile them together, and then we will use the binary cross entropy loss function to for the target versus source site classification. And for that we introduce our custom loss function for the training, because first of all we want our this encoder to have some pre-trained value. So we will pre-train the encoder for the 500 epochs, so that our encoding this XS embedded will look similar to XS, and then we will from this we will initialize and tries to change the value. So this will be more stable and will find for the optimal global maxima and minima. So what happens when we train it in this gain like fashion, and we will make this on the like 3 epochs on the model, and again for the gain like models 300 epochs. So finally we will got these results. So we can see now quite a bit improvement for our domain adaptation methods as compared to the previous models method. And we can see also the individual site results. So each color actually represent a different classifier, we can see in the legend. And also these are the site wise, location wise results. So we can see some classifier perform better for a different kind of site, and also for a different classifier. So the second is also including the class loss. So earlier what we were doing, we were just projecting our data to a similar class, like site, the XT versus XS. But now we also want to discriminate versus HCM MDD, which is healthy control versus MDD patient. So why we are doing that? Because let's say it might happen that it will project our data to some plane in a similar plane, the target and source side, but it is not able to discriminate between healthy and MDD controls patients. So what we do, we have here no updates because we have very less data for our target site. And after this excess embedded, we will back propagate two losses. The first one is the site discrimination loss. So whether it is able to discriminate between site, and this is a kind of our negative loss function. So this loss will be back propagated to improve upon this site classification. And the second is whether it is able to predict between healthy and MDD patients. So this will also a loss which is propagated to this excess embedded, and it will modify the encoder parameters accordingly. So it will tries to maximize this healthy versus MDD patient classification, or also tries to lower the classification loss between XT and XS, which is the target and source domain data set. So here we also add like this one more component, which is our classification loss for this healthy versus MDD, and we will include these loss functions inside our gain training. And we will also do this our custom loss function, because we have now these two y values. So we can see there is also some improvement for the random forest classifier, but still like we need further modifications. And also the same results you can see here. For some classifier it is performing better, and for some it is not performing that much good. So now we introduce something very similar to deep coral loss. So deep coral, we have this similar the classification versus coral loss. But here we are removing this projection of the covariance from the target data set because we have very less data points. So in which what we tries to do, instead of predicting between target and source data set, we tries to minimize the covariance loss between the source and target. So this is actually intuition we got from the deep coral paper. So in which they tries to lessen the covariance between source and target domain, and also tries to maximize the classification versus healthy and MDD patients. So the only difference is we are not using any kind of penalty or kind of a change on the target domain because we have very less data set. So there is no update here, but all the updates are on the source domain data set. So this is our coral loss global. So this is our coral loss, which is actually we got from the research paper of the coral, and we also introduce our MDD the gain like warframe. And finally, our results are these with the domain adaptation methods and for the single site classifier. And also we can see improvement in a few of the sites, and also it doesn't improve for that much of the sites, but there is quite improvement for many of the sites now we can see. So there is also one loss we introduced. So now total in deep coral site discriminator loss, which is our next model, we are introducing three loss functions. The first is covariance loss between source and target. Second is classification versus XS and XT, which is source and target domain. And third is we want to maximize the healthy control versus MDD patient classification. So we defined three these all loss functions together, and now actually the results are not better, actually it's worse because we are now penalizing it a lot from lot of loss functions. So that's why this is kind of a result we can take from it. And conclusion, the introducing too many loss functions kind of didn't help in this case. Similarly for each site. So now we tried the few shot learning to deal our data set because we have very less data points. So to learn from only using very less number of data points. So we have instead of classification, it's kind of a focus on a different kind of thing. It is similarity based approach. So here we we try to predict whether this healthy control belongs to this healthy or MDD patient or not. So it tries to take a data point. Let's say we have a test data point. So it tries to match its embeddings we got from the deep learning model to the healthy controls and also to the MDT patients from all. And it will average the results of this. Actually, there is a result from 0 to 1. So whether it belongs more towards the patient or most towards the healthy controls, and then it will classify accordingly based on a threshold of 0.5. So here we tried both Siamese and triplet loss function, but Siamese loss function didn't perform that much well for the multi-site data set. So that's why we focused on the triplet loss function. So for the triplet loss function, we have these kind of embeddings. So we have a shared CNN weights between the layers, and we have this anchor image. Let's say these two positive image and the one negative image. So it tries to decrease the loss function between them and tries to increase the embeddings weight between the other two. So for that, we need to understand some of the terminology. So hard triplet is actually in which we put some condition that we need our embeddings to at most separable to each other. So we cannot take all our data points because it will bias our data set. So let's say we are taking all of our data points and some are very easy to classify. Then what will happen? It will decrease the overall loss function. So we will select only the points which are hard to classify. So the embedding difference between positive and anchor is actually greater than 0. So this difference. Semi-hard is actually we introduce some parameter alpha. So we kind of lower our threshold. So what data points we actually want to select. So this is our triplet model architecture we made, and using this we can see like there is not that much improvement for the adaptive test balance is actually the balanced accuracy because of the imbalanced data points. So what we did, we modified this version according to our need. So what we did, instead of taking the TensorFlow based data points, the points we want to select, we self-created a model which can select the data points which are of our use. So we made some threshold alpha ourselves and also introduce a model which will create triplet loss function and will select the data points which have this loss function plus some alpha value, and it is qualified for our selection. So whichever data points which actually have a lower threshold, which are very easy to classify, are not taken, but which are easy to classify plus some random batch is selected. So random batch we are selecting because we also want to generalize to our other population. So we do not only want to focus on our data points which are very hard to classify. We also want to take some portion which is generalized to our all our data points, which is kind of a representation of our data set. So also like here we are creating this half triplet. So we are training it in kind of a batches. So first of all, we will take some batches, we will initialize our weight, and then we will select half of our semi-hard triplets, like which are difficult to classify, and half of our random classified, like which are the from the general population. So we can see a quite improvement from as compared to the simple model. So the accuracy increased quite a bit. And also for an individual site, we can see the results actually better than the original model. And also we can see it kind of scatter plot. This is adapt data set. We can see quite an improvement for many of the sites. And also the average accuracy also increased, which is average across all the sites. So now let's move on to the ketamine study. So Abdullah et al. Actually found that ketamine treatment can be used for to cure this major depressive disorder. So we can use it to validate our biomarker for the depression. So first of all, we will study this ketamine 2018 study. So the design of this study is we have the 34 subjects. So they came to the lab, let's say, and they were given some kind of infusion. So the recording is taken before the infusion, during the infusion, and after 24 hours of the infusion. So wherein is actually means the ketamine. So what happens? These subjects were called for let's say 2 different days in a gap of some days, around 13 days. So what happens? On the first day, these subjects, half of them were given the placebo and half of them is given the ketamine infusion. So placebo is actually some kind of an inactive drug. So what happens? We have the recording of this placebo on these 3 recordings, and for the where ketamine infusion study for this 3 recordings. So we have total these 6 different cases. So based on that, we made 13 relevant classification cases, And also we tested them across the 6 atlases on the Schaeffer 100, 200, 400, and also on the norm 116, 216, and 416 across the 25 classifiers. And also we worked with the Hamilton depressing rating scale based on some cognitive questionnaires. So these cases are, each tick actually correspond to the classification case we made. So this tick case one means the classification between placebo baseline versus verum baseline. Similarly for placebo infusion versus verum infusion, and similarly other cases you can see. And also we have these subtraction cases, which means we actually tries to remove the baseline effect by subtracting the functional connectivity from infusion from the baseline. And I will also share the intuition we got. So we can see for just simple classification of infusion, placebo infusion versus verum infusion, we got around 94.5% balanced accuracy, and this is kind of a high accuracy. But the problem we faced is because of this 24-hour classification. So placebo 24-hour versus verum 24-hour, we have just 50% classification accuracy. So this field off because there should be some effect which should remain after 24 hours. This is not actually equals to zero effect we got after 24 hours. So we tries to address this issue. We try to plot the histogram of these different bins actually corresponding to the Z transformed this connectivity matrices values. So we studied it for all the subjects, and finally we introduced this subtraction I talked about. So if we remove the baseline effect, because removing this baseline effect is important. Let's say some subject came on the first day of placebo infusion and just came and take the recording. And on the other day, when she came for this infusion study, the ketamine infusion study, she might took some kind of caffeine, coffee, and because of that, we have a very high baseline. So we want to subtract this baseline, this function connectivity from the 24-hour also, and also from the infusion also. So if we do that, we get a quite an increase in our accuracy with the highest of 67% around. So this is actually improved our results for the 24-hour, and we can see that there is some effect which actually remained even after 24 hours. So till now, I've been talking about kind of a classification results and how we improved our accuracy. But what does it even signify? Because in the starting, I told that I will be discussing some biomarkers. So where are the biomarkers? So biomarkers means choosing some regions in the brain which are related to this activity in which we are focusing. So we do not want to take all the features in the brain and want to classify something. We want to pinpoint the features of importance. So for that we need feature selection. So I introduced three kinds of feature selection. First is linear SVC inbuilt feature selection. Second is t-test based feature selection, and third is random forest based feature selection. So we introduced them based on the, because I tested them across 25 classifiers, and we can see for these classified linear SVC and random forest, the accuracy was quite high. So we used their inbuilt feature selection methods, and also t-test is found to be better for them. Like it is able to find the regions which are significant change in the two classifications. So we can use this as a feature selection too. First of all, I want to introduce the data leakage issue because for our data set, we have a very less amount of data set, for actually 34 for this study. So we tries to divide our data into training and test 90 to 10. And for the cross validation, we further divided the trained data into 90% train and 10% validation. So this will ensure that there is no data leakage. We are not testing on the same data set that we trained on. So this avoids any data leakage issue. So for the linear SVC inbuilt feature selection, actually we tested them across for many feature selection, 500, 1000, 1500, 200, and we found taking top 1000 features of this linear SVC gives us the best accuracy. So I will be discussing them only. And for t-test, we also corrected for the FTR fault discovery rate because we are testing across multiple these features. And also for the random feature selection, random forest based feature selection, we took the all the non-zero coefficients we get from the random forest. So let's discuss them one by one. So this is the code. for the linear SVC based feature selection. So what happens? This is actually just the outer inner loop. So what happens? We have this 10 cross validation fold feature selection, this classification accuracy. Inside it, we have this feature selection. So what you can see here is actually inside just this single loop. You can see NS feature selection linear model. So here, so what happens for this 90 to 10 train to test classification on this training data, we are further cross validating our this linear SVC based feature selection. So we are selecting features on the training data set by further dividing it into training and cross validation. So there is no data leakage here. And how we are selecting them based on the model coefficient, we are getting the feature importance. We are arranging them based on this model coefficient and ascending like in the descending order. So like the importance higher the coefficient means the better the feature is. So the more the weight is, the higher the importance of that feature. So we took only the feature length, which is set to 1000 here. For the t-test, it's we have this, we calculate the p-value and also we put some threshold of this 0.05 after the correction of FDR correction, because we are testing for multiple features. And here we want the minimum p-value. So ascending is equals to true. So it means it will go from minimum p-value to higher p-value, and we will talk the only top 1000. So here we are not talking about the top 1000 actually. We are taking all which qualifies this 0.05 threshold, which is actually a very standard. So this is actually the outer loop. So here we are calling this feature selection. It is doing the feature selection, and you can see there if and else loop and a global variable. Why is that? Because for each and every model, this method will remain the same. It is not actually classified dependent. So we actually wanted to reduce the computational cost, not doing the same thing for each and every classifier, because this is classifier independent. So we are calling it only one time and storing it in a list, and taking all these features numbers and then using them again for each of the models just to fasten our calculation. Similarly, this random forest based feature selection is kind of very similar to our linear SVC based. Just one difference that we are taking, because it makes many of the coefficient to zero for many of the features. So we are taking only non-zero features. Similarly, it is called here. So it will do the feature selection on the training data, no data leakage here also. So we are seeing the results only for t-test. Let's say we can see here we have different feature selection lengths. So this is because for each data set, we are like, when we are shuffling the data set into train and testing, we got different training data points. So each time we have different number of these features which are qualifying this threshold of 0.05. That's why the feature selection is different. And here we have T10 of them. And we can see we have this accuracy like quite a lot, like 86.65 still. This is a summary table of all these feature selection we do. So let me show like each one of them. So these are the 13 cases we made. Then this is linear SVC C1 all fit. Actually, linear SVC with C is equals to 1 is the best classifier we got after testing it across 25 classifier. So we can see this is our baseline accuracy. Then we do some t-test based linear SVC, and RF using only top 1000 features. So last three columns are actually employing only top 1000 features, and the first column is employing the 19,900 features. So we can see this second last method, which is linear SVC C is equals to 1, takes like still have a good accuracy 91.43 from the 94.28, and also we are using only top 1000 features, not 19,019 features. So we have reduced many of our features and still keep the highest accuracy. So that's how we can do the kind of a feature selection and pinpoint the location of the lesions and important features of our brain. And the next like we wanted to do the psychometric effect prediction, so in which like we do not have just the MRI data, we also have the cognitive questionnaires, the amount of the ketamine infusion with time, and like the age and different parameters. So based on these cognitive questionnaires, there are actually 100 of these matrices were created, which actually represent a different kind of experience that person actually experienced during the infusion. So we like for not for all of the subjects we have the data, so that's why we rejected some of the subjects. You can see in the subjects involved, and we calculated different statistics for each one of them. So we can see if we do simple correlation for with the regions and the features, we can see like these regions are highly correlated with this particular this matrices we want the psychometric effects we want to study. And this simple kind of analysis is actually not good, because let's say we got two regions which are very highly correlated to some particular psychometric effect, but let's say they itself are very highly correlated. You can see like visual you can see here, so this first two might be very highly correlated with each other, so we are not getting the regions which are representing different kind of effect. So let's say one visual and one somatosensory, so the importance of each region, so the individual effect between the features should also be taken into account. So that's why we got to connective based predictive modeling, which is CPM analysis. So what it does, instead of taking just one feature at a time, it took all the 19,900 features and put some threshold of let's say zero point 0.2 and select the region which have a threshold of correlation threshold of greater than zero point 0.2, and then it tries to model these predictive these cognitive questionnaires matrices. And we can see like for the OSC score, we have R value, which is Pearson correlation value of 0.44, 0.40 for experience of unity. So we can model all of our these models for different matrices. And also we can see analyze like these regions. These are actually the positive correlations and blue are the negative correlation. But although we actually able to get to very less number of nodes, so here the number of regions are very less. Actually there should be 19,900 connection regions, but here we can see only 100 of them. But still, like there are so many, we want to pinpoint to them as few as possible and still keeping the highest predictive value. So for that, the analysis we done is actually on one of the specific score, which is Oceanic Boundlessness (OSC score), because it is found to be most significant side effect predictive matrix. So what it actually represent is the alteration of the sense of space and time, and also like kind of a mania-like experience. So if person reports high OSC score, it's kind of a bad, means the person is experiencing high psychometric side effects. So because of one of the study, we get like these two brain regions, posterior cingulate cortex PCC and also the parahippocampal cortex PHC region. So this is the analysis they did in their research paper and found that these two regions are highly correlated with this OSC scores. And so from the Schaeffer 200 atlas which we were using, we took these regions which are PCC and PSC region. So on these two, we do two kind of analysis: within connectivity and between connectivity. So within connectivity means, so we have these 8 regions from the Shepherd 200 list. So we do within these 8 region connectivity analysis. So we have 8 into 8 minus 1 divided by 2 regions. So which is 28, 7 for the 28 regions. So using only these 28 regions, we are trying to predict this OSE score using the linear regression and also the lasso for different alpha values and hyperparameters. So we can see for this R2 value, the R square value for the regression is negative. So it is actually not able to predict the OSC score. But for the within connectivity, between connectivity means taking all these 8 regions and finding the connectivity with the different regions. Let's say the PCC1 when its correlation with the other regions, let's say the visual region. So taking all these correlations, we get the 1564 features, and using those 1500 features with the lasso and linear regression and trying to predict the OSC score. So if we do the with the lasso classifier with alpha is equals to zero point 0.1 as a hyperparameter, we get 130 non-zero features, because what lasso does, it tries to compress the weights to zero, which are actually not introducing like significant contribution. And then we get these 130 non-zero features have a very high predictive power towards this OSC score prediction, which is actually quite a significant 0.432 R square value and Pearson correlation coefficient of 0.66. And we also tried to validate the top 10 features on the OSC subscores we had, and we get a, if like this is using all the 19,900 features. If we use the linear SVT to select the best features, it is the, this is the column of accuracy, and this is our manual 10 features which we introduce using this features like this non-zero features, top 10 features. So we can see if we are taking our top 10 features, then we are getting the higher accuracy, highest accuracy as compared to any of the selected features or using all of the features. So that means the features we have had the highest predictability power towards this OSC score. So we can also see the Verum baseline versus Verum infusion differences in the function connectivity. So each point actually represent one of the subject, and also this point is actually the average, like this functional connectivity value for that particular region. So let's say for this 15496, which is this first region, the difference we can see is the kind of some difference. So when we go to the right, the difference actually decreases because this is in arranged to the their order of higher ability to predict this OSC score. Also, we can see this PSC region, which we can visualize here, has a very high predictability power as stated in that research paper too. So we are able to validate their results and show that these regions has a very high predictability power. So that was a statistical analysis, and we are here able to pinpoint the location of particular sub-region. Now let's move on to the feature transfer study. So we wanted the regions which are very related to this ketamine kind of a study. So we have a different kind of effect. So placebo infusion versus Verum infusion versus Verum 24-hour. So we take the intersection of the top 1,000 features between these two cases, and we got 246 features. So what we wanted is we wanted to find the regions. So earlier what we did, we used the PCC and PSC regions, which is actually stated in one of the research paper, and used them to verify our this OSC score prediction. But what we wanted, we do not wanted ourselves to be like constrained by some hypothesis of PSC or PCC regions. We wanted to test across all the brain regions and wanted to identify from the sketch that which regions are actually able to predict this OSC score side effects with a high accuracy. So what we did from this Ketamine 2018 study, from this classification study of these two cases. So here the each case is actually the subtraction from the baseline. So we took the two cases which are very highly related to our ketamine infusion. So if we take the top 1,000 features from placebo infusion versus Verum infusion, and Verum infusion versus Verum 24-hour, and if we take the intersection of these features, then we are only retaining the features which have the highest effect on this ketamine infusion part. So we are taking features which are very highly correlated to the ketamine infusion. So when we do this regression for the OSC score, we get like for the 2018 study we have the OSC score, and for the 2014 study we have the CADSS score. So if we use these 246 features with the lasso zero point 0.1 alpha, then we get the highest regression score. So the first column is actually the Pearson correlation coefficient. Second is R square value. Third is the feature length. So this manual feed means the feature selection, inbuilt feature selection, which we are not using any kind of a bias like the 246 features we are taking. This is just based on the feature selection of the inbuilt feature. But this is our 246 features which we found, and we thought that these have the highest classification and regression actually value for the OSC score. And we can see that our hypothesis is actually correct. and these 246 features which we get from the ketamine infusion study is actually able to highly predict these OSC score for the 2014 and also for the 2018 study. And actually we tested this for the various classifier, and we got we learned that lasso is actually performing the best. And we also, like, these are the results we can see. So using the 246 features we selected, we getting the Pearson correlation coefficient of 0.688 and R square value of 0.443, and this line is actually our regression line, and these points are actually the actual values. So, and also if we visualize the function connectivity matrices, like what is the difference, then we can see like there is some significant difference for each of the features. We can see here which feature name is actually corresponding to. It is actually two regions because it is actually the function correlation value between these two regions. And also we did the gradient analysis. So this is some other kind of verification we wanted. So what we wanted to test that these 246 features we got is actually having some significant differences in the gradient also. So this gradient analysis is actually very similar to the PC analysis, and what it tries to do, it tries to compress the data, and based on having the highest component which have the highest eigenvalue, we select only those components and rejects the very low eigenvalue component, and that way we can do the this gradient analysis and take only the most significant components. So the intuition for this analysis actually came from one of the study by Teng et al. And they showed that for the autism spectrum disorder, there is some kind of no interaction between these visual and DMN network for this ASD patients. So what happens, like for normal subjects, there is interaction between the visual and DMN function connectivity, but there is no interaction between visual and DMN regions. So we did this analysis for our data also, for the ketamine data, and for this we actually aligned all the gradients, and we analyzed for the top 10 out of the 246 features, and we were actually able to see some differences in the functional connectivity of these, like the gradient component differences of these top 10 features of the 34 subjects. To visualize this, we have plotted all these regions using the BrainNet software from the MATLAB. And these red line actually correspond to the positive correlation, and blue is actually the negative correlation with the OSC score. So these regions are actually able to predict this OSC score, and these are actually the gradient components. The last one is the ketamine depression study. So we have these all the results, so we wanted to verify them in some study, like on some different study, which is ketamine depression study. So what happens in this study is we have all the these subjects, MDD patients. So here all of our subjects are actually the patients which are suffering from the major depressive disorder. So they came into the lab. They were infused with ketamine, and the recording was taken during the day in which the ketamine was infused, and after the 13-14 days of the this ketamine infusion. So actually, the ketamine is given in some regular intervals, and we wanted to know whether the depressive patient actually feels some improvement or not. And we had different ratings based on some cognitive questionnaires, so HAMD, HAMA, so and Marder's score. So Marder's is more related to this depression, and HAMA is actually more related to the anxiety score. So we created this Y value using the K-means clustering into responders and non-responders. So we have 13 non-responders and 21 responders. So we wanted to, first of all, like the first task was to classify between responders and non-responders. So for that, we actually got a 72.5 accuracy, balanced accuracy. So we took the function connectivity value from all these subjects and subtracted it from the baseline, and then classified whether that person responded or not responded to the ketamine. The next was the regression, because this is actually not 0 or 1. So what we wanted to know, if we are able to predict whether that subject able to respond to the ketamine or not able to respond. So it is not actually 0 or 1 as I stated, but it's actually some improvement. Let's say some has a rating of 8 and other date as a she has a rating of 10. So there is some improvement. So we wanted to regress this Marder's score. So first of all, we used only the functional connectivity values from the baseline to predict this Marder's score, and we were not able to do that. And then we used only the final value, and then able to this predict this Marder's score, and still not able to do that. But when we subtracted the functional connectivity of the final and removed the effect of this baseline, then we were actually able to predict this Marder's score. So this is just a simple analysis that this is just a baseline. So we are taking all the 19,900 features and we are using them to predict the MARTEST score, whether this person will be able to respond to the ketamine or not. So the importance for this study is actually we are giving the ketamine infusion to the person who might not respond, and still there is some side effect which are going to get along with that person. So we are giving some kind of a negative thing to that person, so we wanted to avoid that. So we wanted to first hand predict whether this person will be will be responding to the ketamine or not, so that person might not have to go through this procedure or get some side effect too and not getting some improvement. So we wanted to find out the regions, and we wanted to test it our regions we got from the 2018 study on this, whether they are able to predict this ketamine responders or non-responders. So from the intersection of this feature, top 1000 feature from 0 and 1, which actually represents the regions which are more related to ketamine. So here we are not focusing on the ketamine infusion regions, but on the ketamine regions which have any kind of effect on the ketamine. So we take the intersection of top 1000 features of the 0 and 1 index, and we get the 66 features. So if we take these 66 features out of the 19,900 features, and then we try to classify the responders versus non-responder, then we get a highest accuracy of 80%. And if we use the classifier own selected features, then we get a highest of only 67.5. So we can see thus our 66 features that we selected from the Ketamine 2018 study have the higher predictive ability of 80% as compared to any of the features that are selected by inbuilt classifiers. Also, we did the regression analysis using these 66 features, and we found that still, like in this regression case also, our 66 features are performing much better as compared to any other features we take. Like this is the algo based same feature selection which are performing even worse, and this is our 66 features that we selected from the Ketamine 2018 study, and these are performing much better even as compared to baseline and even as compared to the classifier's own selected features. So to just visualize, like finally we wanted to visualize which features are there in the brain region. So these are the regions these correlation features are corresponding. So these are the non-zero features which we get from the lasso, because we wanted to visualize them. So we needed lasso to get only the most important features. And we can visualize the differences in the functional connectivity between each of these features for each of the subject. And finally, we wanted to visualize the regions which have the highest impact on this MDD prediction and the ketamine effect. So the regions here we are getting are in the visual cortex. So these are the regions which have the highest impact on the visual area. So as when someone is infused with the ketamine, we know that person actually experience some kind of a hallucination. So this is actually justifiable. And also there are high correlation regions in the these are our DMN network, default mode networks, because it is thought to have some effect in the depression study. So that way we are able to find the biomarkers which have been the effect of the ketamine on the depression. And actually each node, this breadth of the each node, actually this line you can see is actually the importance. So higher this width we can see is means the more the importance of that feature have. So the conclusion is we are getting actually 3 papers. So the first is the conference paper which is already been submitted for the OSC score prediction in ketamine. And for the other, I am working with the Professor Meng, Dr. Meng, and Lina on the PCC and PSC regions on the ketamine study prediction. And we are expecting a manuscript by the June mid. And I am also working on another manuscript on the MDD results prediction, and we are expecting the manuscript by the June end. So these are the references I used in the slides, and thanks.